So yes, today I'm going to skip all of those years that Nobel mentioned and tell you about what we're doing today. What we're doing today is always more interesting than yesterday, because you understand what you did yesterday and what you're doing today you don't understand. That's why it's fun to be science. I'm going to tell you about plastic solar cells, and specifically I want to focus on this issue of self-assembly of bulk heterojunction nanomaterials by spontaneous phase separation. Now most of this, unless you're already in this field, you won't understand the title. I'll tell you what a bulk heterojunction is. Nanomaterial, I think you know. And of course, phase separation is ubiquitous. It's all over the place. Peanut butter is phase separated. Mayonnaise is phase separated. So if you have two semiconductors which phase separate, then you have something special. Because when you have two semiconductors that had an interface, you have a heterojunction. So if you can get spontaneous phase separation in a mixture of two semiconductors, then you have heterojunctions everywhere. And heterojunctions, for those of you who are not familiar, are analogous in some ways to p-n junctions. They separate charge. And so it's that feature that we're going to be using. And let me begin by showing you just some photographs. This is an image of some plastic solar cells made at this company, Canark. I'll use the name many times throughout, I presume. This is on a rooftop in Massachusetts. They're just checking the lifetime. You can get a little bit of a sense of it, not very well. These are very thin, they're very flexible. You can make them sufficiently thin, and with different polymers, you can make them with different colors, that you can actually see through them. Okay? You can see here this shadow right through, there's a car here somewhere. Here, you can see that. So I want you to imagine that sometime in the future, instead of build the windows on big buildings just having a color filter on to prevent the glare and the sunlight from coming in, we'll use that sunlight and convert it to electricity. Here's an example of that. This is a real example. This is a demonstration project, of course. It's in Florida. And at a company called Arch Glass. This is generating electricity every day, and it has an inverter on it, so it goes AC, and they feed it into the grid. Now, if you want to convert sunlight into electricity, there are 3 steps. It doesn't matter really what the material configuration is. There are 3 steps. First step, of course, is that you must absorb the photons in a material. We're going to use sunlight, we're going to use photovoltaic effect, we're going to try to convert sunlight into electricity. So we have to absorb the photons. Now, one of the reasons that these polymer semiconductors are interesting is because they have very high extinction coefficients, very high absorption coefficient. That means you can make a very thin film. Okay? That means you don't need to use very much material. It means the material cost can be minimized. Now this is really 19th century chemistry. German dye chemists taught us how to make high extinction coefficient dyes that lasted a long time. We've learned a lot since that time, and we have still, as you will see, a lot to learn still, but the origin of this idea of high absorption coefficient, high extinction coefficient, absorption of photons, is chemistry of the 19th century. Now the next thing we have to do is we have to separate charge. photon is a neutral entity, is going to promote a molecule or a molecular entity into an excited state that's a neutral system. So somehow I need to get charge separation that is generated, or it's photo-induced charge separation. I think it's quite clear that that was 20th century physics, 20th century chemistry. Rudolf Marcus was awarded the Nobel Prize in Chemistry for theory of photo-induced electron transfer. And then our work came some years later where we demonstrated that you could actually get photo-induced charge separation on remarkably fast timescales that are 1,000 times faster than the first step even in photosynthesis. The third step in the making of a solar cell, in photosynthesis, what you want to do is you want to take the separate charges and you want to use those separated charges to generate a chemical reaction. You want to make food. Okay? But we don't want to do that. We want actually to collect those charges at the electrodes. And in order to do that, we need to have a degree of self-assembly which is quite demanding. And I'll try to show you that in detail. And I would call that 21st century physics and chemistry and material science. These are problems that we're really working on today, and problems where, very honestly, we don't know what we're doing. This is a very old image of half a dozen semiconducting polymers in solution. It's made to show you 2 points. One is that different polymers have different molecular structure, they have different electronic structure, and they have different colors. Those of you who are spectroscopists can read off the energy gaps of these things just by looking at the colors. But the other point, of course, is that I want you to realize that these are not just colored liquids. I want you to think of them as inks, and inks with electronic functionality. I want to think of these as polymers that are semiconductors or metals that one can print and therefore print with electronic functionality. People all over the world, scientists all over the world are printing displays, they're printing integrated circuits, and they're printing solar cells. And that was, of course, our dream, that we could actually do something like this cartoon suggests, do a roll-to-roll coating to make plastic solar cells, and that's happening. So this is a photo of a plant in Lowell, Massachusetts. It was originally a Polaroid plant to make photographic film, multi-layers on film. We need multi-layers to make our solar cells. It converted directly and it's quite effective. You can see here, this is the roller. It's about 6 feet wide. This right here is the section that we're actually using, because if you use the whole thing, you have to waste a lot of material when you're just learning how to do it. So this is capable of running at 30 feet a minute and 6 feet wide, and can generate a huge amount of photovoltaic material. Now, Jean-Luc mentioned polyacetylene, which is of course the one that's right here on the top. And as time went on, more and more of these conjugated systems have been developed. This is not even close to a complete list. And the systems that we're working on for photovoltaics are not on this slide. But I just want to give you the impression, and the real impression, that since synthetic chemistry has come into this in a big way and has made many materials available to us today with a variety of functionalities and a variety of specific parameters, for example, to change the energy gap of the semiconductor, to change the electronegativity. These will be important specifically in this problem of plastic solar cells. So why am I interested in plastic solar cells? Well, I'll give you some reasons aside from just the intellectual interest. Printing is a very low-cost manufacturing technique. Print newspapers, you print magazines, and so it is. I haven't verified this, but I would assert it's probably the lowest manufacturing method, if not certainly one of the lowest in real cost. It's also very low energy, low in energy cost, not just low in dollar cost, but it's low in energy cost, and that's particularly important these days, as you know. It's also, because of that, leaves a very low carbon footprint. I'll give you some numbers. So there's too much on here to look at in great detail, but notice that with a crystalline silicon, it takes 2 years to pay back the energy that you expended in making the solar cell. Okay? So for the first 2 years, I'm happily changing sunlight into electricity, but I'm only paying off a debt. Whereas for the flexible OPV, this number obviously is sensitive to the efficiency. So I think here it was assumed, just to make the point, efficiency of 7%, I think it was, but you see the point. It takes not 2 years, but 2 months. Okay. So and these others are interesting. Cadmium telluride is better, but not a whole lot better. SIGS is even more costly in terms of both energy and CO2. As you saw in that image, everything is done at room temperature. There's no high temperature. Nothing needs to be melted. Nothing needs to be heated to high temperature. So the cost is just the cost of running that roll-to-roll. This is my favorite picture of a demo. This too is a real image. It's in Florida. This is a little parking lot. These very simple structure without much mechanical integrity is being used to give shade. That's fine. But now we have on top of that these plastic solar cells all over it, generating electricity according to the area. Beautiful idea. And it is beautiful, actually, not just as an idea, but good looking. And again, you can imagine architectural interest in this kind of thing. To build this into buildings because of the flexibility. I should comment that the flexibility is not necessarily so much that you can bend it, although I am bending it here, but it's really very rugged. Okay? You can throw these things around and they work. I have one I forgot to put in my bag, or I would show it to you now, but I carry it around in my bag, and the TSA pulls it out and they look at it, and I've been carrying it for 3 years, and it still works just fine. People talk about taking pieces of this kind to Africa or to India or to places where there is no electricity, and that one such unit, one such small unit would change the life of a family. A lot of that, there has been some serious attempt to do that, but they tend to break. Silicon solar cells are very brittle. SIGS is very brittle. Cadmium telluride is very brittle. The roads are not very good, and I've been told, I've never tried to do it myself, but that the survival rate is really low. So the ruggedness, this non-breakability associated with the flexibility is particularly important. All right, so maybe that makes it interesting to you. Let's talk about the science, the physics and the chemistry that underlies this concept of a plastic solar cell. Well, step one is the absorption of a photon, and I'm showing you here a cartoon of a photon coming in and being absorbed by a semiconducting polymer. If that semiconducting polymer happens to have nearby a neighbor, a fullerene, then one gets electron transfer at a time scale of 50 femtoseconds. That is to say, 1,000 times faster than the first step in photosynthesis. To do that, to use that, rather, I should say, one needs to create a new kind of material. A material where I would like you to think of the fullerenes on the black material, and the polymer is the white material. So we have two interpenetrating networks of materials, both of which are percolated, that is to say, both of which are fully connected to the top and the bottom, so that I will be able to get charge out. The idea then is, of course, that I photoinduce an electron transfer from here to here, which means from a white part to a black part, and then the electron goes out that way and the hole goes out on the white. That's the idea. And that is happening all through the thickness of the film. Those heterojunctions are created, so therefore we call it a bulk heterojunction material. These heterojunctions are not made, that is to say, I don't get in there with my fingers or with some fancy instrumentation. They form by spontaneous phase separation. Polymers always tend to phase separate. There's no entropy of mixing. But that's only the beginning of an understanding, or hardly that, even that. But suffice it to say that through self-assembly, we can make materials of this kind, and as I'll show you, it's rather general, and we can collect charge in that way. Okay, so here's another diagram. This is a physicist diagram of the photoinduced electron process. So I'm going to come in with a photon. I'm going to promote the electron to the lowest unoccupied molecular orbital, and I'm going to get charge transfer to the nearby fullerene. Okay. You say, well, look, the charge transfer is pretty straightforward. I push the electron up here, and I gain a lot of energy, or I should say I give away a lot of energy in that charge transfer process, and that's true. And what we'd like to do is we'd like to minimize that loss. We'd like to actually bring this LUMO up as close as possible to this LUMO, so the offset is small, but just large enough to get the charge transfer. Although I show you that here in a cartoon, it happens at 50 femtoseconds, and that's shown in great detail in this beautiful piece of work, which I won't go over in any detail here. Okay, so 50 femtoseconds, I keep using the number. What does it mean? Well, the question is there any competing process? And of course there are some competing processes. We try to make a list of them. The one that seems to be the closest is the luminescence decay. But we know that time scale is hundreds of picoseconds. So that's 4 orders of magnitude slow. So the real impact of this 50 femtosecond number is that the charge transfer is quantitative. Every photon that comes in leads to a pair of separated charges, an electron on the fullerene and a hole on the polymer. And at least in one case that I'm very proud of, we've been able to collect all of those charges. We don't want to lose them. We work hard to make them, so we want to collect them. And the limitation on collecting them, of course, is the morphology of the material. Well, the question is, can you make this kind of a material? And the answer is yes, and I'm just going to show you a little bit of electron microscopy to convince you of that. In this particular case, what we've done is to use polythiophene, poly-3-hexylthiophene with the fullerene, more or less drawn to scale. This ring is comparable size here. And we've just mixed them, and we've cast a film of them. And when you do that, you get this structure. If you anneal, you get this structure. And let me just focus your attention on this structure, which is quasi-equilibrium structure. After annealing for many hours, it stays this way. And you can see the fullerene black parts going over significant distances, and you can see the polymer lighter parts. The reason the fullerene is darker is not because I chose it to be. It's because there are more carbon nuclei per unit volume in the fullerene than there are in the polymer. The electron comes through, makes many small angle scattering. That makes the velocity of the electron beam slightly slower, and we're using that in this phase contrast imaging to make the polymer dark, the fullerene dark and the polymer lighter. Now, this is looking top down on the cell. What I really like to do is I like to cut a cross section. So I'll use a focused ion beam to cut a cross section, and another one, and I'll take that thin cross section, and you can believe me that I've never done this, but I have some students who have, and who have very good hands. And you can take those very thin sections, they're going to be 60 nanometers in thickness, and you can put them on an electron microscope grid, and you can image them. And here, for example, is what you see. Now, the data are here and here, here and here. This is for a 120 nanometer thick slice. This one is thinned down to about 60 nanometers. A little hard to see. We purposely just enhanced the contrast. This image to this one, this image to this one. We know that we have 1-to-1, approximately 1-to-1 of the fullerene with the polymer. So we just made the volumes that we see here equal. That sets a threshold, and very easy to do. But you know, there's no cheating. I mean, let's see. Let me just find something that I can recognize. Look at this structure here. You see it very nicely here, and you can find it all over. Okay. So this is a bulk heterojunction material. Okay, this is 100 nanometers thick, or in this case 60. And you tend to form these, in this case, fortunately, a morphology which is column-like. You notice that I'm losing this thing here. Right here, there's a heterojunction. Right here, there's a heterojunction. This one's particularly nice. You know, you see a continuous pathway all the way across. That's a solar cell right there. That heterojunction forms a solar cell. Here's another one. Here's another one. It looks like that one doesn't connect to the electrodes, but I don't believe that. I think if I took the next slice and the next slice, I would find that this thing wanders up and connects to the electrode, and almost all of them do. Now the wonderful thing is that I can do the spectroscopy for electrochemistry, and I can find out the energies of the HOMO and LUMO of the component materials. And I can predict what the open circuit voltage should be. I'll show you how to do that in a minute. Just from that spectroscopy. And when I make the macroscopic system, when I make the solar cell that I showed you the photo of, I get the right answer. So that tells me something which is simple but profound. There are about 100 billion solar cells here per square centimeter, and they're all hooked up in parallel. Just think about it a second. The only way I could get the right answer on the macroscopic system from the energy levels of the molecules is if they're all hooked up in parallel. And I don't understand that. But it's nice, very nice. I can take this system and I can take, of course, all digital information. So I can take a scan across here, and scan across here, and scan across here, and take all that data and I can average it and I can start doing some calculations. I can calculate, for example, the intensity here times the intensity a little ways away, and then I can integrate over that separation. That's called the autocorrelation function. And here's a plot of the autocorrelation function from those data. Okay. Autocorrelation function, of course, starts off at 1, because when the 2 points are at the same place, then they're correlated. But the question is, how fast do they fall off, and is there any semblance of periodicity? And there is. So it falls off here with as you can see, in nanometers, 10, 15 nanometers. The repeat length is about 25 nanometers, and we've seen this kind of thing now in several systems. Okay? So those are the typical numbers, 20, 25, 30, and I'm sure this is one number, but a distribution of numbers on that scale. That's the length scale that the phase separation forms spontaneously. It's interesting, I can make that structure in more than one way. Let me try to, I don't want to get too deeply into this. The way typically we do that is we just take a flask and put in a common solvent both of the components, and then simply shake it up and then cast the film. And there's another way you can try to do it. You cast one film of one material, then you put the other film on top of it using a solvent which is not a solvent for the first. And then you anneal it, let things happen. And the answer is exactly the same nanostructure, whichever way you form them. See in more detail there. These are indistinguishable. So this fact that I alluded to, that this spontaneous phase separation forms these bulk heterojunctions in many materials, and that with the same general characteristics, and that I get to the same final state from several different routes, suggests that this is not just an accident, it's not kinetically limited, but this is the actual minimum energy state for this these two component systems at obviously over some temperature range. Again, a conjecture that is not understood in detail. People are becoming much more sophisticated, and you all know you can go, if you should ever need to the hospital and have a MRI scan. What they do is they create a three-dimensional image of your brain, and then in software they can cut slices through it, and you've seen those, you're fully familiar with that. Well, you can do that with you can do that with electron beams as well. The way you do it schematically is you have your sample, and the electron beam is coming down this way, and you tilt it this way. Then you tilt it this way, being always extremely careful that you don't move the middle point. And then you construct a three-dimensional image. Then you can do tomography. And I'm showing you just one example of that here. Japanese colleague from Sumitomo. This is an electron tomographic image of a polymer that was not disclosed, but you can see just beautifully these pathways that over long distances. Here's the projection angle. So understanding and first of all, finding methods for studying morphology are critically important, and then understanding and controlling morphology is something which is still certainly not understood, and in some sense is the holy grail of the field. All right, now that's how I make the material. Now I want to make a device. The device, in fact, is really quite simple. I want to put this bulk heterojunction material between two electrodes so that when I come in with a photon and I separate the charge, electrons will go to one side and holes will go to the other side. In order to do that, I have to tell the electrons which way to go, because up and down are the same. So I break the symmetry simply by using two different metals, a low work function metal on one side and a higher work function metal on the other side. And the electrons will always go toward the low work function side, and the holes will go to the high work function side. So the fabrication is simple. On the nanoscale, it's done by spontaneous phase separation, and on the macro scale, it's done by using two different materials for electrodes. Now, of course, I'm purposely exaggerating, but the essence of what I said is true. Okay, now let's talk about how these solar cells work. I'm shining light on. I showed you what happened. When I shine light on, I promote an electron from here to here, and then I get transfer. So if I have a reasonably bright light, let's say 100 milliwatts per square centimeter, which is what I have at noon in sunlight, sunny day, and I have quite a few electrons here, holes here, and quite a few electrons here. The numbers turn out to be around 10 to the 16th per unit volume. Okay? So in fact, that sets the Fermi level, or the chemical potential, of the holes here, and it sets the Fermi level, the chemical potential of the electrons here, and that gives rise to a built-in potential between the two, and is that which gives rise to the solar cell function. That built-in potential actually drives the carriers out to the external circuit and into useful electricity, and I'll show you some more about that later. But the essential number, so I would like to always try to make my donor and my acceptor such that the energy gap of the donor will be fairly small, so I can absorb the full solar spectrum, which goes all the way out into the infrared. And we know that silicon does that very well. So I'd like a solar spectrum which is in fact close to that of silicon. And I'd like to make this energy as close as possible to this one. So I'd like to bring these sort of together with an offset that is just sufficient to enable the charge transfer. Those are the tasks of the synthetic chemist, to make the polymers which will do that. As I said, we're trying to build in some of the units that the German dye chemists taught us about in the 19th century, but getting all this right in a given system is not a trivial task by any means, and we've not yet succeeded in doing that. All right, this is the way the solar cell is, let's say, is evaluated. I multiply the short circuit current, that is the current when I have no load, times the open circuit voltage, that's a power. Now I don't get all that power. This says for any battery, there's a maximum power point. This is a solar battery. So I can only get this fraction, the green fraction of the total of energy out. So that means that the efficiency that I can hope to achieve is a product of the short circuit current times the open circuit voltage times this fill factor, the ratio of these two areas divided by the input power. So I need to address these three parameters. I need to make this big. I just told you how to do that. I need to make this big. This is, this depends largely on morphology. And I need to make this big, and this depends on recombination and morphology, and I'll come back to it. So all this is pretty much understood. Really, the physics, the device physics is not very different from inorganic solar cells. And one can sit down and one can write down those equations, and it's been done in this paper to calculate what efficiencies we might hope to achieve with this technology. And of course, you have to make some assumptions, and if you say, I really make a perfect system without, you know, the Luon offset is nearly zero, and et cetera, then you would follow this curve. This is as a function of the band gap. As I said, the band gap for silicon is about here, about where? About here. And indeed, if you make the gap smaller, you get more efficiency. And eventually you start losing because all the carriers relax at the bottom of the band. But it's an interesting number, it's 30%. Well, it's unrealistic. We can't ever make it that perfectly. But without trying to prove it to you, I honestly think we can get into this regime. And surely this one is accessible to us. So I'm telling you that I think we should be able to achieve polymer solar cells, which are in the range of 15 to 20%, or maybe even higher. And I'll show you where we are in a minute. Well, this is where we are in the sense of what's happened over the years. These things were first discovered in Santa Barbara in 1995. Efficiency was less than 1%. And over the years, gradually increasing, my hope is that not only is the first derivative increasing, but that the second derivative is increasing, because we still have a long way to go to get up to 16 to 20%. But it's very interesting that today we can make 8.5, we, the community, can make 8.5% efficient solar cells in the laboratory, not on that roll-to-roll system, but in the laboratory on this scale. So it's legitimate. It's getting up there and improving, and my guess is that within a few months we'll see 10% and onward. Here's an example of some work that we did a couple of years ago. It gives us a 6% solar cell. By now, this is no longer a record breaker, but it's interesting because in this particular system, we were able to show that that the internal quantum efficiency was approaching 100%. We could show that every photon that was absorbed gave rise to an electron-hole pair, and that we collected all of those. Now, not quite all, but more than 90%. And that's an important conclusion. And it allowed me then to say, well, okay, if that's true, we should be able to estimate what efficiency we really could get by an experiment. Okay? And the experiment is shown here. This is basically the spectrum. This energy gap is much too large to be optimum. This red light is coming through. So let's go here to the green light, right in the middle of the absorption spectrum, and let's make a solar cell that will test it with monochromatic green light. You get 17%. Just as the theory suggests we should.